Alright, so I accidentally stopped that video, but we'll just have two videos for this. So, moving on. It says recall the absolute value of x is the distance from between x and 0 when x is positive. So when you plug like a 2 or a 3 in for x, absolute value of x is still x, it's equal to x. But when x is negative, your sign changes. So if you have the absolute value of negative 3, that's going to equal the opposite of negative 3, or negative 3, which is positive 3. So that's what this part means right here. It says when x is less than 0, when x is negative, the absolute value of x is going to be the same as negative x. So if I plug in negative 3 here, it actually equals negative 3, which is positive 3. Just a fancy way of saying that it will always be positive. This is the piecewise definition of the absolute value function. Transformations of the parent absolute value function are also piecewise functions. So to start, your piecewise function of the parent function would look like this. So it would be x when x is positive, so when x is greater than 0 or equal to. Again, this is one where the equal to can go in either spot, but it's negative x when x is less than 0. Okay, so if we want to use transformations, we just need to transform each of these pieces. So for your new function, we'll call this one p of x actually, for parent function. So f of x, your new function, we are going to move everything right 1 and up 3. So we're going to do the same thing to this. So it's going to be 2, because you're going to stretch it by 2. You're going to go right 1 and up 3. So it basically stays the same, except your boundary point's going to move as well. So because it started at 0, you're going to move it right 1, up 3, but it's still at x is greater than or equal to positive 1. The 3 doesn't really matter because it's moving vertically. So you're just looking at the negative 1 there to figure out your boundary point. And then this one down here is going to be x is less than 1. Now for the negative piece, that negative really, with the absolute value functions, we only care about changing the horizontal aspect because like this plus 3 right here, it's not going to go into minus 3 because then those two functions wouldn't match up. So really, we're just going to apply that negative to the negative 2. So it becomes negative 2, x minus 1, still plus 3, and that is, so it shifts up 3 to meet with this function right here. And that's for when x is less than 1. So basically, you just change this part right here, the plus 3 or whatever your vertical shift will be doesn't change, to a negative. Okay, next. Okay, next we have what we call a step function. So we talked about that a little bit earlier. It says step functions are piecewise functions. A step function pairs every number in an interval with a single value. The graph of the step function can look like a step of a staircase. One step function is called the greatest integer function, where it has this y equals bracket x. It also looks like this as well, where it just has the bottom foot, I guess, where the bracket x represents the greatest integer, less than or equal to x. It's also sometimes called a floor function, which is why the feet are on the bottom. You also have what you call a ceiling function, which works the opposite of this, which has the feet on the top, because it's a ceiling. But I'll talk about that in a minute. Okay, so when you're graphing that, basically, we'll go up to 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So basically this, like it says, the bracket x represents the greatest integer that's less than or equal to x. So if we plug in, let's start with negative 3. The greatest integer less than or equal to negative 3 is negative 3. If you just plug in whole numbers, it's actually pretty simple, but when you plug in decimals, that's when you actually see what the function looks like. So if we plug in negative 2.5, the greatest integer less than or equal to negative 2.5, that's going to be negative 3. So you can see that everything between negative 2 and negative 3 is going to go down to negative 3 until you get to negative 2. Then it becomes negative 2. But if you do negative 1.5, it's still going to drop down to negative 2 until you get to negative 1. Okay, so our graph will look like this step function. Negative 3 is going to be a closed circle. Closed circle. And it's going to have the same value until you get to negative 2. So then we put an open circle there, and it jumps up into negative 2. Until you hit negative 1, then it jumps up. And 0, then it's going to jump up. And so on. So we get this step function is what we call it. Okay, and that is known as a floor function because you're rounding down, basically, to the lowest integer. Okay, if it were a ceiling function, this negative 2.5 right here would go up to negative 2, because you'd be rounding up, not down. And these you can transform just like anything else. So if you're doing 2 times that, basically, if we keep the same graph right here, or same table, and we keep all the same x values, negative 3, negative 2.5, negative 2, negative 1.5, negative 1, basically all this this 2 is doing is multiplying all your y's by 2. It's a stretch, a vertical stretch. So all these y's are going to double. So we get negative 6, negative 6, negative 4, negative 4, negative 2, and so on. So this graph would look like this. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 1, 2, 3. Okay, so this graph would look like this. You'd basically just be going to negative 3, negative 6, closed, open. So instead of jumping up 1, this one actually jumps up 2. So it goes up to negative 4, open circle, up to 2, open circle, up to 0. Notice 0, 0 still the same because it's 0. Open circle, up to 2, open, and then up to 4, open. So the stretch basically just doubles the length of the height of the step, I guess. So yeah, and that's a step function. Okay. Okay, so this one says, each piecewise function can be considered a parent function. Piecewise functions can be transformed by translating and stretching the function just like other parent functions. Recall that g of x equals f of x plus k is a translation of the function f of x up k units when k is positive. When k is negative, the translation is down. Similarly, g of x equals f of x minus k in the parentheses is a horizontal shift, left or right. And finally, g of x equals k times f of x is a vertical stretch or shrink by a factor of k, with a reflection if k is negative. So with this one, this is what is the graph of, it gives you the graph of f of x, it doesn't actually tell you what it is, but it wants you to shift it down to, see, because that is on the outside, it's a vertical shift. So basically you just shift all these points down too, and it will look like this. With an open circle there. And then this one shifts down too, so it starts here actually. It goes like this. And that is with a closed circle. So that one just shifts. And again, you can shift it left or right. If it was like f of x minus 2, that would shift everything right 2. If it was 2 times f of x, that would just times all your y values by 2. If it was a negative, it would reflect everything. You times by 2 and then reflect everything. So yeah, the transformations work the same with the piecewise function as any other function. Okay, and that is all of the piecewise function stuff. So make sure you guys do Camps quiz, and I'll catch y'all on the flip side. Adios.